All right, well, good morning, and I'm honored to be here to have the opportunity to speak to all of you. This is my second visit here. I met many of you when I was here about a month ago, and had the opportunity to look at the facility and the work that you were doing. As Frank said, my goal is not to really lay blame anywhere. What I want to do today is educate people about the causes of corrosion. Instead of really just teaching you how to avoid it, I'd rather you know something about it so that with a little bit of education, you can identify issues that might be causing corrosion on your own, again, rather than just being taught how to carry out an assembly to avoid it. So knowledge is power. I will emphasize also this is, I don't want you to hesitate to ask questions. If I say something that you don't understand, or that you have a question about, please don't be shy about asking questions. I welcome it. It's an opportunity for everybody to learn. If you're thinking that question, there's probably 10 other people thinking the same thing. So again, please don't hesitate to ask a question if you're not sure. If you have cell phones, I would ask that you just silence them, please. Okay, let me give you a little bit of background about myself. I started out in this industry as a boat builder, essentially, working as a marine mechanic and electrician, and did that for about 7 years. I've been a consultant in this industry to the boat building and repair and manufacturing industry, as well as for boat buyers, for about 15 years. I managed boat yards and custom boat building shops for about 12 years. And a journalist in the marine industry as well, a technical journalist for 28 years. I've been in the industry overall for 34 years. So this is what we'll look at today or this morning. Different types of corrosion: galvanic, straight current, crevice corrosion, which is peculiar to stainless steel, which you may see some of with stainless steel fasteners and other hardware. Poultice corrosion, which is unique to aluminum, so that we're going to definitely spend time on that. And I'm going to do a second presentation this morning, a little shorter one that's specifically about aluminum corrosion. And we'll talk about something called dezincification, which is peculiar to copper alloys. And then finally, I'll do some myth busting. I find in this industry, the subject that it has the greatest level of misunderstanding, bar none, is corrosion. When I read posts on the internet from boat builders or boat owners, or when I receive emails from boat builders, the questions that I get about corrosion are far and away the ones that embody the highest level of misunderstanding. And that's not a reflection of the people asking the questions. It's an indication of just how seemingly mysterious corrosion is. It shouldn't be. It's science, it's physics, it's electricity in many cases. But there is a lot of misunderstanding about it because it's all taken on faith. You can't really see anything that's happening. It's too small for us to actually understand why. So to have a better understanding of it is a better way to avoid it. But again, there's a huge amount of misinformation about it. So I'll talk about some of the things that are most misunderstood about corrosion and try to help clarify those. So one of the most common types, or probably the most common type of corrosion that we see, is something called galvanic corrosion, also known as dissimilar metal corrosion. And that occurs at a relatively slow pace. It takes months or years for this to occur, and it is the result of two different types of metal that are sort of unfriendly to each other. And the two most common types of dissimilar metals that sort of create this style of corrosion, and in its worst example, are aluminum and copper. So building aluminum boats, as you folks do, you have to be sensitive to that. And this can occur even from a few strands of copper wire that fall into the bilge of an aluminum boat and are then exposed to an electrolyte, which is water in our case, that can lead to pretty significant corrosion. So attention to detail and sort of good housekeeping in aluminum boat building are really important because, and I'll show you this in a minute, but we use a scale called the galvanic series, which is a list of every metal Aluminum is really low down on that list, meaning it is the most corrosion prone, and in the presence of almost any other metal, it will corrode. So pretty much anything that you let touch aluminum, any other metal, except for two other metals which are more corrosion prone, and those are zinc and magnesium, anything else that comes into contact with aluminum and is in the presence of an electrolyte, which can be just atmospheric moisture, you will end up with corrosion. Some of it is worse than others. As I said, copper alloys are especially unfriendly to aluminum in that kind of a scenario, like copper wire, but almost any other metal will cause this to occur. So here's the galvanic series, and you can see that magnesium and zinc and aluminum are way up there at the top, or the most corrosion prone, what we call least noble metals. And down at the other end of that, we've got gold and titanium and graphite, and then eventually stainless steel. The further apart the two metals are on this scale, the more likely they are to interact with each other. One of them will suffer. So if you took graphite, for instance, which we use sometimes as a lubricant in some cases, or some bearings have graphite impregnated in them, and you put that in contact with aluminum, the corrosion rate is going to be really significant. Carbon fiber, for instance, is an example of that has graphite in it. If you put that directly in contact with an aluminum substrate and it gets damp, even, doesn't have to be wet necessarily, the corrosion rate of the aluminum is going to be really high. So our goal is to try to use metals that are closer to each other on the galvanic series. Now that's not always possible. We're not going to source, aluminum fasteners to use in aluminum, although we do that occasionally. We're going to use stainless steel. We just have to be conscious of the fact that if they are touching each other directly and they are wet or damp, then corrosion can occur. Now here's a good example of this, a bronze sea strainer that is attached to an aluminum bracket. Again, it doesn't have to be submerged, just has to be in a damp environment, a high humidity environment. If that high humidity also has salt, sodium chloride ions in it, that's going to accelerate this process. It will occur in the presence of fresh water, but salt water accelerates it because of the conductivity of seawater. So again, and you can see if you look closely, the aluminum is what's suffering, not the bronze. The less or least noble metal of the two is going to be the one that's going to suffer as a result of this. In this example, we've got a stainless steel fastener that is in an aluminum track, and so those two making contact with each other, and water penetrating between that interface between the two is problematic. Adding to this scenario, though, is the fact that it's a recess. So water that leaks into this area, or let's say that it's exposed to water in this area, the water is essentially trapped. It is sitting in a puddle at the interface between the two different metals and exacerbating this problem. So recesses like this, where it's a depression and water can pool there until it evaporates, adds to this issue. If it's seawater, then what's happening is the seawater is evaporating from that area and leaving behind the salt. So you end up with almost a brine solution in an area where you've got two dissimilar metals that are already unfriendly to each other. It makes this even worse. So where possible, we try to avoid traps where water will be in a horizontal area where water will be trapped and sit there for longer periods of time and then evaporate and again leave salt behind. So just making that worse, and you can see the aluminum track here, which is anodized, but it's corroding where it's making contact with that screw. Now, stainless steel fasteners are a fact of life in boat building. We're going to have them, and we've just got to live with it. There are ways to mitigate this that I'll talk about, but primarily what we try to do is to fill the gap between a stainless fastener and an aluminum substrate with some type of material that'll exclude water and air. So if we can do that, we're going to slow this process down considerably. The metals don't necessarily need to be in direct contact with each other for this process to happen. So if water is dripping off of a copper alloy plumbing fitting onto an aluminum substrate, you can end up with this type of pretty severe corrosion. Again, it's fairly slow, but it will happen. So if you had a copper or a bronze pipe that was carrying seawater for engine cooling, and it had a slow leak and it was dripping onto an aluminum hull, you can end up with what they call salts of copper coming out of that, little microscopic bits of copper falling onto the aluminum and resting there, and then causing this type of corrosion. This is I don't know how well you can see this. This is a good example of this. This is a bronze raw water pump, and it's got a slow leak, and it's dripping onto that aluminum support structure, and it's actually corroding away that aluminum just from the copper that is coming out of the off the pump through the seawater leak. So again, they don't necessarily have to be in direct contact with each other. The most problematic combinations, as I said, copper and aluminum is among the worst. Stainless steel and aluminum also. Manganese bronze, for instance, which is really a brass alloy because it has zinc in it. So manganese bronze and stainless alloys like propeller shafts. So for an inboard application that used a manganese bronze propeller and a stainless shaft, you could end up with issues on the manganese bronze because it is less noble than the stainless steel. So one of those is going to corrode. Now, here's an example of a good type of galvanic corrosion that we actually take advantage of, and that's using an anode or a zinc. That is exactly this entire process. In a nutshell, a sacrificial anode is being used to protect other metals. So the same sort of scenario is going on in a beneficial way. The anode is less noble than all of the other metals that it's protecting, or it should be, and it's offering that protection, which is why it's called sacrificial. So again, just as an example of how this is working in a way that benefits us, sacrificial anodes do that. I know you guys don't see bonding systems like this because you're building aluminum boats, so they're essentially already bonded, but just from an understanding perspective, one of the goals that we have in a fiberglass application is to bond the dissimilar metals together, essentially connect them with a wire, a low resistance connection that is then connected to a sacrificial anode. That anode will protect any of the metals that are bonded in that system. The threshold for the interconnection of these metals from a resistance perspective is very low. It's 1 ohm for the electricians out there. So we really have to make sure that the contact between the metal that's being protected and the sacrificial anode is very good. Now that holds true for an aluminum vessel as well, in that if an anode is being attached to the hull and the connection is dirty, there's paint on it, there's corrosion on it, there's marine growth, and it is more than 1 ohm of resistance between that anode and the hull, we have now compromised the ability of that anode to protect the hull. So that surface needs to be extremely clean. Again, 1 ohm is a very low threshold for corrosion. Dan?
So yeah, we are doing fiberglass hulls. Is this just for hull penetrations under the waterline?
Yeah, so good question. So Dan is asking, because you guys do some fiberglass.
We do a lot.
You do? Okay, my mistake then. I thought it was primarily aluminum. Is this just for penetrations below the waterline? Well, from a corrosion perspective, yes. Anything above the waterline that gets bonded is bonded for other reasons, for electrocution protection, for lightning issues. If it's a submerged metal, like a through-hole fitting, a strut, a thruster, any of those get bonded for corrosion protection purposes. So in the world of corrosion, we have 2 approaches, which I'll talk more about in a minute, but just this is a good time to mention this. We either isolate all those metals completely, or we bond and protect. Mostly the bonding and protecting is the way that this is done, because not only does it offer the corrosion protection, but it's also an electrocution protection issue and a lightning issue. So typically we see underwater metals getting bonded and then connected to a sacrificial anode. Now, if you bond them all and the anode goes away, the next least noble metal is going to start to corrode. So if there's something in that mix, for instance, something that has zinc in it, like a manganese bronze, that's going to begin to corrode. So that's why it's so critical to to maintain the anodes. The anode replacement interval, just while we're on this subject, is when it reaches the 50% depletion mark, it needs to get changed. A lot of people operating vessels like these will look to save some money, and they'll wait until the anode is almost gone, and that is a mistake, because as the anode corrodes away, its voltage potential drops. So it's not offering as much protection as there's less of it, as the weight of it drops. So 50% is the accepted sort of threshold for replacement, and that's something that your customers need to understand, and I think that is in your literature that you supply. Okay, well, it should be. Don't be cheap about changing anodes. All right, other ways to offer protection from a corrosion perspective, a galvanic corrosion perspective, is something called a galvanic isolator, which I think you do use on some of your boats. If the vessel has shore power, if it can be plugged in dockside, when the vessel gets plugged in, the bonding system or the hull, let's say if it's an aluminum vessel, and if it's fiberglass, then the bonding system, all the underwater metals are now connected to everything else that's plugged into that same dock through the grounding system. So even if the power isn't turned on, when you plug that vessel into shore power, the safety ground is connecting everything that's submerged, that is bonded or metal, to everything else on every other boat that is in that marina, unless there's some way of blocking that or on that dock. A galvanic isolator blocks DC and allows AC current to pass. And the reason for that is if there's an electrical fault on the vessel, an AC fault, a shore power fault, we need to let that power pass through so it'll trip a circuit breaker and render that fault safe. So we don't want to block AC. But DC is what corrosion comes from. So that is often misunderstood. People feel like, well, I plug the boat into shore power and then I'm seeing more corrosion. It must be the shore power. It's really not. AC, for the most part, with very rare exceptions, does not cause corrosion. DC does. So if we can block the DC, the galvanic isolator becomes one way of doing that. And my philosophy is if the vessel gets plugged into shore power for 1 week out of the year, as little as 1 week out of the year, it needs to have a galvanic isolator or some means of blocking potential interaction between that boat and other boats on the same circuit, on the same dock that are nearby. Now, while that approach is good, it's not foolproof. The galvanic isolator can be overwhelmed if the corrosion, or if the fault rather, has high enough voltage, it can get past that galvanic isolator. So it's sort of for average scenarios. If you want more protection, the solution becomes something more absolute, like a isolation transformer, which is depicted down there in the bottom photo. An isolation transformer completely separates the shore power from the vessel. There's no physical contact between the two anymore. It's utilizing a transformer, something called inductance, that transfers the electricity. There is no ground connection between the boat and the dock. So in that scenario, the protection level is absolute from other vessels. Okay, you can still have corrosion on the vessel that originates on that vessel, but you can't have something that is coming from another vessel that is plugged into the same shore power system. So if you need that level of protection, or you want that level of protection, an isolation transformer becomes the means of doing that. It's larger, it's heavier, much heavier, and it's more expensive, but it does work. And it offers some other benefits as well, including polarity issues. If the polarity on the dock is reversed, there's a fault in the electricity coming from the dock, the transformer will correct that. So it does offer some additional benefits in addition to isolating the ground from the dock and the boat. It is a polarity correction device. It also reduces the likelihood of electrocution for people in the water around that boat. If the boat is equipped with a transformer, that becomes much less likely. So again, several advantages to a transformer, but from a corrosion perspective, it's an absolute disconnect between the vessel and the power on the dock and other vessels around it. All right, the other type of corrosion that we are concerned about is called stray current corrosion. So I like to say if galvanic corrosion is like a turtle, stray current corrosion is the rabbit. It happens really quickly, in some cases in a matter of days, as opposed to months or years like galvanic corrosion, which proceeds much more slowly. Stray current corrosion comes from, as the name implies, current that's coming from a battery. So it's coming from the vessel's own DC electrical system. In some cases, it can come from the DC electrical system from a vessel nearby, but in most cases, it's originating on the boat that is suffering from the corrosion, and the power source is a battery and or battery charger. And because the current is so much higher in stray current corrosion, that is why it is so much more rapid. So again, you can put a hole in an aluminum vessel with stray current corrosion, again, in a week or two, if the current level is high enough. So pay really close attention to that. And that comes primarily, well, that's an example of it, okay? So that's a stainless steel propeller nut, and you can see it's sort of pitted. The evidence of stray current corrosion is usually sharp edges. So it's happening so rapidly that the metal is being removed, and it almost looks like as if it's been eaten by a worm in some cases. It has a very sharp feel to it if you run your finger over it. So if you see evidence of that, it's usually a very clean surface as well, because metal is being removed rapidly. Now, if stray current corrosion occurs and then it stops, that surface will become oxidized. It can even get marine growth on it. So don't let that fool you. If you see evidence of that, and it happened in the past, it'll slowly sort of lose that evidence over time, because it's going to turn a different color, and again, you can get marine growth on top of it. But if it's still ongoing, it's going to be a clean, sharp surface, and it's nearly, in 99% of the cases, it's submerged. It's underwater. It's not occurring where you can see it necessarily. The primary source of this type of corrosion is wiring that is in or near the bilge. And what is that usually? It's a bilge pump. So wiring for bilge pumps and the actual bilge pumps themselves, they're sitting in bilge water. They have electricity connected to them. And unless that is 100% isolated from the bilge water, then you can get leakage of that current into the bilge water and the source for stray current corrosion. So in this case, this is a bilge pump that was causing stray current corrosion. It actually had a fault within the pump, so you couldn't see it. But when I took the pump apart, I was able to identify that water had leaked into the housing of the pump and was now making contact with the energized portion of the pump when it was running, and leading to stray current corrosion. So again, bilge pumps and bilge pump wiring. So the wiring for bilge pumps necessarily has to be in the bilge. That's impossible to avoid. So we need to be extremely careful about how that wire is routed, how it's terminated, how we make connections like this. I don't know if you can see that, but I've actually separated that butt splice from the wire just by tugging on it slightly. And even if I didn't, that butt splice is anything but waterproof. So if water gets on that connection or it gets submerged, it's going to leak current into that bilge water, and it's going to look for a path back to its source. Electricity is always trying to return to its source. So if it's a battery, in this case, it's going to travel through the water in the bilge. It'll go to a through-hole fitting and then back to something else that is bonded, a propeller, for instance, or another through-hole fitting, and then ultimately back to the battery. And it's going to damage one of those metals in the process. It's going to remove it, essentially. So the wiring for bilge pumps and any wiring that is near the bilge just needs to be absolutely meticulously installed, and if it's a connection, it needs to be waterproof, essentially. It cannot just be a conventional butt splice that's a few inches above bilge water, because it could become submerged. For bilge pumps, my preference is to use a pump with a really long lead on it so I can make those connections well above bilge water if possible. So some pumps do a better job of that than others. This pump, the wiring for this pump that I'm looking at here is over 60 inches long, so it gives you plenty of room to make those butt splices well above the possibility of ever being submerged in bilge water. If you can't achieve that for some reason, then again, the butt splice needs to be completely waterproof. Now, does that mean using a heat shrink butt splice connector? It could, but you have to be cautious about that, because if the crimping die, for you electricians, Sparkies out there, if you use a crimping die that is too aggressive, it can actually pierce the insulation on that butt splice, and when you heat it, that pierce opens up into a hole. So you've defeated that waterproof or let's say insulation on that butt splice. So if that's occurring, then you need a different means of waterproofing that connection. It could mean crimping it, heating it, and then looking for those holes and filling them with a sealant, or going to a less aggressive crimping dye. Something has to be done to keep that butt splice completely waterproof. If you can't, again, achieve this well above bilge water type connection scenario. So when bilge water does make contact with wires that are energized, you'll often see this sort of pinkish result where it is freely corroding from straight current corrosion. If you see evidence of that, you know that's not a good scenario. Electricity is leaking essentially into bilge water and causing this kind of damage. Bilge connections, bilge pump connections here, again, I don't know if you can see this, but I'm holding a ruler into that bilge, and that terminal strip is about 9 inches above the bilge water and completely exposed. So really not an ideal scenario. My rule of thumb is if I can't make those connections at least 18 inches above the bilge water, then they need to be completely waterproof so that there's no possibility of current leaking into the bilge. All right, so let's move on to something called, any questions about that before we go into stainless steel? Does that all make sense, everybody?
Is that something we should be testing? Like, after, I guess if our connections are high enough,
Yeah.
then we don't have to test.
Well, so the question Dan's saying, is it something that can be tested for? Actually, you can do corrosion testing. You can do something called reference cell testing that you would do if you wanted to establish a baseline on a vessel to see if it's being protected by its anodes, or if you suspected some problem. But from a bilge water or a bilge wiring perspective, I don't think you need to test it. I think you need to just eyeball it and make sure, again, that any of those connections are well above bilge water, and if they're not, completely waterproofed. And that doesn't always mean just a conventional heat shrink butt splice. The crimping die plays a big role in that, and how aggressively it gets crimped, and whether it actually puts a hole in it when you heat it. That can be tested, and should be, and then it should be done the same way every time. So testing in that respect, yes, but testing for leakage, I don't think you need to do that unless you suspect a problem.
But we should do the silver anode test on new boats.
Yes, so the reference electrode test, in my opinion, should be done on every new vessel so that you can establish a baseline. So once the vessel goes out into service, if 6 months later they report a problem and you do another reference cell test on site and it's much different, you know something has changed. So you knew when it left here, it was right, and that something got changed along the way, or a fault occurred. A wire has chafed against a fitting and it is now leaking into the hull. That can happen as well. Yeah. Okay, so crevice corrosion is the most common type of corrosion that attacks stainless steel. Now, for stainless steel to remain corrosion resistant, it needs exposure to one thing primarily, and that's oxygen. It needs air. When it is exposed to air, it develops a very resistant oxide film that keeps it stainless, essentially, that keeps it from corroding. If you put it into an environment where it is robbed of air, where it is, if it's in stagnant water, for instance, so there's no dissolved oxygen in the water, or it's making contact with something that is wet and keeping stagnant water against it, like insulation or even fiberglass in some cases, then that stainless steel can go from what's called passive to active. It can stop being stainless and start acting more like conventional metals. So this fastener, the shank on this fastener, you can see it's what we call hourglassed. That is where that fastener passed through a fiberglass hull. Water penetrated into that void and remained there in a stagnant fashion. It wasn't being turned over, so the oxygen in it got used up very quickly. And now that stainless steel doesn't have exposure to oxygen anymore, and it becomes active and begins to corrode. The dangerous part of this scenario is the parts of the fastener you can see look perfectly fine. The head and the threaded end, the parts that are exposed to oxygen, so they're doing okay. But the part that's inside the area where it's passing through, and a hull again in this case, is crevice corroding. That's a sort of dangerous kind of scenario because upon inspection, everything looks fine. This fastener was actually attaching a propeller strut to the bottom of both, so pretty high stress scenario and one that's really important, but didn't know that it was a problem until it was removed. Now, you might have some telltale evidence of this. When crevice corrosion occurs, it usually creates a brown staining, sometimes called tea staining or coffee staining. It's a dark brown, typically sort of a rust stain that will emanate from that stainless steel fitting. So if you see this sort of drip or trickle or line of rust coming out of a stainless fitting where it passes through some structure, that should definitely get your attention. It means that stainless has gone active, at least in some location where it passes through that substrate. So that's the only clue you're going to get that this is going on. Don't ignore it. It's absolutely worth looking at more closely. Now, that's a good example of it on the underside of a deck. This happens above the waterline as well as below. So stainless steel passing through a substrate that can trap water against it in the void, or because the substrate is hydroscopic, it can hold water like wood, for instance, is a perfect scenario for this. Now, here, this is a good example of why it's not a great idea to bed the inside of a fastener. If you use sealant around the nut side, the part that's inside the boat, you're creating a trap for water to get stuck inside that void. So bedding or sealing the outside, whatever you're using, whether it's a polyurethane sealant or mastic, fine. We know we need to do that on the outside to keep the water out, but do not put anything on the inside because, again, that can create sort of a plug that will trap water in that void and lead to, or maybe exacerbate, a crevice corrosion type scenario. A keel example in this case that uses stainless fasteners, that water leaked into that interface between the two, and that brown, pretty aggressive or blatant example of this, but all that brown staining that you see there is an indication that crevice corrosion is going on in a pretty big way there and should not be ignored, especially in a high stress scenario like this. Now, even the highest grades of stainless steel can be susceptible to this. So if you look closely at this, you can see that that's labeled 316, which is one of the more corrosion resistant versions of stainless steel. But if you rob it of oxygen, again, it is going to eventually suffer from this scenario if it's exposed to water as well. So sometimes there's not a good solution to this. If you're building an aluminum boat, you don't want to use copper alloys like bronze because that is harmful to the aluminum. And sometimes stainless is the next least worst scenario, and you're sort of stuck with it. It's just something that becomes a maintenance item. The people operating the boat need to be aware of the fact that the stainless steel could become active and crevice corrode. And again, that brown staining like that is the telltale, the warning that this has gone active and is corroding freely. Hose clamps are notorious for this type of failure, especially what I call a T-bolt clamp, the type of clamp that you would use a socket wrench to tighten. It has a nut on it rather than just a screw head. Those are made up using a flap of stainless steel that traps water. Again, notorious for this, especially if it's in an area like near a bilge or even in a bilge. Water getting into that flap between the two pieces of stainless on the clamp, like the one that's shown here, sets up a perfect environment for crevice corrosion. How can you prevent this on a T-bolt clamp? There are some T-bolt clamps that use an interlocking feature rather than a spot weld, and they tend to be less susceptible to this. Alternatively, before the T-bolt clamp is installed, it can be saturated with a corrosion inhibitor like CRC, heavy-duty corrosion inhibitor, that penetrates into that fold and fills that void with the corrosion inhibitor, keeping the water out. That's been my approach to that. Stainless steel is also susceptible to something called stress corrosion cracking. So microscopic cracks develop in stainless steel that is stressed, like an application like this where it's a chain. That stress crack is a void. Water leaks into that void. It's stagnant once again and begins to crevice corrode and expands the crack because of that corrosion. So I suspect in a scenario like this there would have been a lot of staining before this actually failed. You'd see evidence of it and know that it was occurring. But it is in stressed stainless steel scenarios. A conventional hose clamp is well known to do this as well, right where the threads are located, the perforations for the threads. You'll get microscopic cracking. Water enters those cracks and begins to corrode. To the extent we can, we don't want to cover up stainless steel. We don't want to paint it if we can help it. And we don't want to cover it with things like plastic because water penetrates beneath those coatings and comes into contact with the stainless steel, again, becomes stagnant. The oxygen gets depleted, and then the stainless steel goes into an active mode. So this is a lifeline, a coated lifeline that has PVC coating on it. Water has penetrated beneath it, and you can see that brown staining. That's an indication that the stainless is crevice corroding there. So the solution there is use uncoated wire so that you don't have that entrapment type of scenario. Another stress corrosion cracking scenario for stainless steel. So you can see the head of this fastener actually separated from the shank, probably after being torqued. There's some microscopic cracking between the head and the shank. Water penetrated into those cracks and exacerbated that situation, so eventually causing that fastener to fail completely. Stainless steel wire, even if it becomes dirty, interestingly, can be subject to this crevice corrosion scenario. The dirt can actually hold water between it and trap water between the strands of the wire. So in this case, there's a little tiny brown spot there that caught my attention. And when I clean that wire, I can see that that strand of wire was beginning to crevice corrode. It's got pitting in it. So this is actually a piece of stainless wire that was covered with a PVC, not a coating, but a PVC tube that kept it wet all the time. Dirt got into there. There was probably some what looked like green mold or bacteria as well that was growing, and that kept the environment damp and oxygen depleted, and it eventually led to pitting corrosion on that wire. Questions about any of that? Does that make sense to everybody, that scenario for stainless steel where it's wet much of the time, the water's not moving, there's no air being exposed to it, and you're going to end up with this sort of crevice pitting type corrosion scenario? Does that make sense?